commercial nuclear fusion relies on a fuel cycle that does not yet exist in the West. Tritium fuel must be bred in situ using enriched lithium-6. Currently, China and Russia control 100% of global industrial-scale enrichment capacity. This geopolitical monopoly creates an immediate vulnerability for Western fusion startups. Global demand is projected to scale from 0.5 metric tons in 2024 to 5 metric tons by 2030. At that point, demand will exceed total non-Chinese and non-Russian supply by over 1,500%. Even with planned Western pilot facilities, domestic capacity will reach only 2 metric tons by 2036. This leaves a net global deficit of over 6 metric tons. The Western fusion transition is fundamentally bottlenecked by this single point of failure material. The physical design of a fusion reactor's breeding blanket dictates its raw material requirements. To maintain self-sufficiency, reactors must achieve a tritium breeding ratio above 1.05. Failing to meet this threshold results in rapid fuel depletion and reactor shutdown. High-enrichment designs like molten salt blankets require 99% enriched lithium-6. Producing the 25 metric tons needed for a single reactor startup requires 1,100 metric tons of natural lithium feed. This assumes a standard 50% process yield. Scaling a modest fleet of 20 dual-coolant reactors would require 200 metric tons of pure lithium-6. This volume represents nearly 40 years of current global production capacity. The material requirements of these designs expose a massive scale gap between physics models and industrial reality. The primary barrier to establishing domestic enrichment is chemical and environmental. The only proven industrial-scale method is the column exchange, or COLEX, process. However, COLEX requires over 1,000 kilograms of elemental mercury per kilogram of lithium-6 produced. This extreme toxicity makes relicensing COLEX impossible under modern environmental frameworks like the Minamata Convention. Western developers must therefore rely on unproven alternatives. These green technologies, such as laser isotope separation, remain stalled at low technology readiness levels. Furthermore, these alternatives impose a severe energy penalty. Laser separation increases electrical consumption by 1,400% compared to COLEX. Achieving reactor-grade enrichment without mercury will require thousands of cascade stages and massive capital investment, keeping the West dependent on foreign supply for decades.